Let's talk about non-removable discontinuities of the jump kind. So what we have here is we have a jump discontinuity, and there'll be a certain part of the domain of the function f. So this blue curve is the function f. There'll be a certain part of the domain, let's say the value c. So we'll take a look on the x-axis at the value c. And at the value c, what's going to happen is we're going to look at what's happening as x approaches c first from the left. So as x approaches c from the left, it looks like what's happening here is as x goes towards c from the left-hand side, it would look as though the value of y is approaching this y value right here. Let's call that y value L1. So we say, use this notation to say the limit as x approaches c from the left of f of x is equal to L1. We also want to know what happens as x approaches c from the right. As you can see, as x approaches c from the right-hand side coming along this curve, it actually looks like we're approaching on the y-axis this value, which I will dub L2. So using the notation, we can say the limit as x approaches c, and the plus means from the right-hand side, of f of x is equal to L2. So we have that the limit as x approaches c from the left-hand side, the little minus as a superscript, of f of x is equal to L1, while the limit as x approaches c from the right-hand side of f of x is equal to L2. So my left-handed limit and my right-handed limit equal two different numbers, two different y values, L1 and L2. So I can conclude that overall, the limit as x approaches c of f of x does not exist, because in order for a limit to exist, it has to approach the same number from the left side and from the right side. All right, so the example I want to look at is the function f of x equals the absolute value of x minus 2 over x minus 2. What I'm going to do is I'm going to make a table of values to see what's happening as I approach the value where the discontinuity is, because if I plug in 2, the f of 2, this is going to be 2 minus 2 in the denominator and 2 minus 2 in the numerator, which is one of the indeterminate forms. So what we're going to have to do is we're going to see what happens as you approach 2 from the left. So here's 2 on the x-axis. That's the value 2. And we're going to approach 2 from the left. So I'm going to plug in a number like 1.9. 1.9. The numerator will be 1.9 minus 2, which is negative 0.1. But when I take the absolute value, that'll amount to positive 0.1. But the denominator will be still negative 0.1. So as I'm approaching from 1.9, the y value is going to be negative 1. And if I plug in 1.99, a number still on the left of 2, but a little bit closer, the numerator is still going to be positive because of the absolute value is going to be 1.99 minus 2 is negative 0.01. But the absolute value of negative 0.01 is, of course, positive 0.01. But we're still dividing by negative 0.01. So when I put in 1.99, oh, I get another negative 1. So it seems like we have a constant function here on the left side that only takes the y value negative 1. Let's try one more. 1.999. 9. That's even closer. So 1.999, even closer. 1.999 minus 2 is 0.001, negative 0.001. When I take the absolute value, I'll get positive 0.001. Then I divide that by negative 0.001, and I once again get negative 1. So it seems as though from the left-hand side, the values of y, as I approach 2 from the left-hand side, are always a constant negative 1. So it seems like I have a constant value of negative 1 coming all the way from the left, all the way to the value of 2 on the x-axis. So as I'm approaching 2 from the left-hand side, it seems as though the values are always going to be negative 1. Well, let's see what happens if I approach 2, in this case, from the right-hand side. So we're going to need to plug in numbers that are bigger than 2 now, but progressively getting closer to 2. So I'll start with a larger number than 2, like 2.1. And if I plug in 2.1, 2.1 minus 2 is 0.1, and then the absolute value of 0.1 is 0.1, but then I'm dividing also by positive 0.1. That's going to give me the value 1. If I want to get a little closer to 2, I can do 2.01. And if I plug in 2.01, 2.01 minus 2, 0.01, positive. The absolute value of that is also positive, and the denominator is also positive 0.01. So here again, I get positive 1. And as you can see, there's a pattern. If you plug in 2.001, you once again get positive 1. So as I approach 2, this is interesting, as I approach 2 from the right-hand side, it would seem as though I have constant values of positive 1. Positive 1. So what I have here is that the limit as x approaches 2 from the right-hand side of f of x is equal to positive 1, and the limit as x approaches 2 from the left of f of x is equal to negative 1. Finally, I can say that the limit as x approaches 2 overall of f of x does not exist. So I write D, N, E.